Hello and welcome to the demo 3 of µRTE. My name is Thomas Bart and I'm the creator of µRTE. It is assumed that you already have seen the introduction video as well as the first two demo videos, because what we will do today will be based on what you have learned in those other videos. In this video we will have a look at the other demo projects and talk a little bit about other features or additional features µRTE offers. For this video I will use the µRTE plugin version integrated into STM-Cube. In the previous video we made an LED blink, and this model now, as it is shipped as an example project, is basically the extended version of this blinking LED. So my idea for today is that we will simply walk through this model a little bit and discuss the structure of the model as well as the features of µRTE a little bit. So what has changed, or what is within this model, is that in addition to our already known LED software component, we now have an additional button software component. Within this button software component, let's make that a little bigger, and we can reset origin to make it go on top. Within this software component we have a runnable, which is triggered every 200 milliseconds and which will read out a button state from this hardware interface button signal, which connects to an in-driver called button read. And within run read button, this in-driver is then called through the signal and acquired also with every execution, so every 200 milliseconds. And then 3 outgoing signals are sent out from this runnable, which represent the button state as a Boolean type. So is the button currently pressed or not? This is a so-called event signal. So this is fired whenever there is a positive edge on the button, and this event signal then can be used, for example, for runnable activation. And there is an outgoing signal called button count, which contains the number of seconds the button has been pressed. So first of all, let's have a look at the code. So up on top there are always the drivers, and then a bit lower we'll find the runnables. So let's have this side by side. We can see the trigger port. We can see the read button tick. So this is the name of this trigger port. This will be passed in here. We can see the ingoing hardware in button, the hardware interface for the button. And we can see the 2 outgoing data signals, button state, button count, as well as the outgoing event signal, button edge. First step to process the data is to acquire the hardware data with a pull port in and get. And once we have our button data, we can directly set the button state signal, because the button state signal is just the same data basically as the hardware in button, we could also reuse this hardware in button signal, but from my perspective it's a cleaner design if we separate the hardware interfacing signals from the application data signals. Also, in this simple demo, they all have the same data type, but it might make sense to put some more ideas or a little bit more thoughts into how to also structure that in terms of data types. Yeah, because, for example, you might want to have something like an invalid state or so forth. I mean, like this could be also handled through the signals, but it could make sense from the application point of view to have this also as a valid data type. But as I said, I want to keep this one simple, so they are basically all simply Boolean data. Yeah, and that's the reason why we can simply acquire the hardware button data from this ingoing signal and simply pass it to button state by simply calling set. Now, if we want to detect edges, or if we want to count how long the button has been pressed, we obviously need some kind of memory to remember if the button had been pressed in the previous cycle. For that, I've created a global variable, and global variables in µRTE are also modeled to give the possibility to the generator to automatically generate the task protection sets, but also to have those global variables traceable. So how this was done is simply for this runnable new child global variable, press count, it has a description. It has to be assigned to an output section, so where it will be stored in memory. We have to give an initial value literal in here, and we have to define a data type. And what will happen is that the declaration of this global variable then will be generated above our runnable, or it depends on how it is configured. Now in that case it is a static variable within the runnable, but it is generated as user code. And the reason why it is generated as user code is because it might be, for example, a C++ object, and then it's not that easy anymore with how to initialize, how to call the constructor, and so forth. So that's the reason why it is generated as user code with the expected signature and so forth. And it is the responsibility of the user to make sure that this piece of code here, or this declaration, still is in line with the attributes coming from the model, and to make sure that this global variable is according to the specification. And with the help of this global variable, we can now detect edges, because if the button currently is pressed and the current count value is 0, then we will have, or then we've just detected a positive edge. And all we have to do for the event signal is to call this trigger method so that this signal gets triggered. For the button count signal, the global variable, which is of type uint16, is set, but the signal type here for this signal was set to button count. And now if we want to translate from one data type to the other, and we do not want to do this within the runnable, we can simply define this uint16, so the data type of the global variable within the runnable, as an alternative input type. And what this will do is that for this signal, so for the button count signal, this will create a scalar method within the signal. So we can now use the alternative input API, so set uint16 to set this value, and this will do even a little more, at least in my implementation now, because I will now translate also this uint16, which represents the number of ticks. So remember, this button is called every 200 milliseconds, and translate that into seconds by simply dividing it by 5 and setting this as the signal value. So the idea of this scalar here is value in is the value as the user wants to set it, or if this scalar is used with an in driver, then this is the driver value. So value in is the ingoing value, and we have to translate into pointer value signal. So this now shall be the new payload of the signal, and with the return value of the scalar, we can indicate to µRTE if this scaling operation succeeded. The next thing I want to show, let's start from scratch here, is how to pass data in a meaningful way. Because this run read button is executed every 200 milliseconds, and if we now want to process it on the receiver side, we might have the problem that if we would simply call this runnable every 100 millisecond, that this runnable comes before the other runnable. And now there are several possibilities to avoid such races, but especially in safety critical systems, we need a good approach and strategy to make the behavior deterministic. So the first possibility to adjust the behavior is to give a trigger order for the trigger port. However, this trigger port order always refers to the task within in which the runnable is executed, or the trigger port executes. So the problem with that is this trigger here executes in the button task, while this runnable here executes in the LED task. So this trigger order cannot be used. This only works if you have multiple runnables being due at the same point in time within the same task. Another approach could be to use the on data event of this signal here as a time base. However, the problem with that would be that the button state signal refreshes every 200 milliseconds. So this runnable now would run with a time base of 200 milliseconds, which is against our specification. And the third possibility to control this behavior is to give an offset to the time base. So the number here, or directly in the configuration, the offset here defines how much this this period is shifted. So by giving it an offset of 2 milliseconds, we can make sure that the run LED is always executed after the button time base. And also what we can do with the offset is to create a system which behaves in a time-sliced manner, as it is known, for example, from aerospace safety standards. To make sure that we always work with the latest data, now the age can be restricted for this particular signal. So the minimum age could be set to 2, but in that case we can leave it also to 0. But we can define a maximum age of 102 actually, but to allow a little bit of jitter, I defined it here as 105 milliseconds. And if now the signal cannot be acquired by run read button, and basically within button state we have old data, then the get operation for button state would return an signal to old return value, so that within the run LED we only respond to new data. All right, let's explore the model a little further. And let's have a look at the UART functionality. The functionality of this UART is also represented in the logical function model. So we can see we have a button which is influencing our controller, which will create UART frames that are then sent to a PC, and within the requirement model there is a specification on what this UART should do in detail. I'll now present it from the data flow perspective, in which the button count as well as the button state signal, as we have just defined it, is passed to a UART software component. And this UART software component contains a runnable run UART send, which is triggered every time there is a new button state signal. And if you remember, the button state signal is refreshed every 200 milliseconds, which means that also this runnable now will execute every 200 milliseconds. Also, remember, you can have as many trigger ports as you want. The functionality here is, as soon as the button is pressed, the UART runnable shall send out strings basically through UART, which indicate how long the button has been pressed already. The problem here, however, is that the strings going out theoretically can be of arbitrary size. Also, another problem is that the signal itself would contain basically the buffer for the outgoing message, and then you have a lot of copy operations. So you have the runnable in which the string is compared, then it is copied into the signal, and then later on it might be copied to hardware, which again is copying it into some internal memory. So this might be not very efficient. And what I want to show with this example is how to grant pointer access to the signal so that we can directly use the signal payload. However, this of course is critical and should be avoided, especially in safety critical systems. In such systems we could for example, do the driver call directly within the runnable, and I will go to show that in a minute, but first of all I want to show how to use the pointer access feature of data signals. So in order to allow that, we have to mark or to tick the allow pointer access flag, and this will then change the API of the signal a little bit and unlock additional methods. In order to use this feature, we first have to create a pointer. So a pointer to the payload. For that, we can use the pointer type of the signal class. And if we have this pointer and it's not initialized, we pass it to the getPointer method. And we pass the pointer to the pointer, so the address where the pointer is, to this method. And this method will initialize the pointer to the location of the payload, and it will also change the state of the signal so that no concurrent modification can take place. If the pointer now contains the valid address, we can write data to this pointer. And once this has been done, the pointer has to be released again. For that, the pointer is passed to a method called releasePointer. Within that method, the pointer will be invalidated, so you cannot use it afterwards. It's invalid then. And also the signal verification will take place, and if the validation succeeds, then this release pointer is the equivalent basically to a set operation. So, and if this all worked, then a push port out can be called so that the data as it is right now in the signal is passed to hardware. As I just mentioned it, as an alternative to pass the data through an hardware signal, we could also do the driver call within the runnable. However, we need to make sure that the generator is aware that we do such hardware access so that it can grant the access rights for that. And the way this is done in µRTE is through so-called protection sets. So in this example here, we can see there's a protection set called UART, and this protection set now contains a reference to the peripheral UART. Also, we could put more information in here. So for example, if our driver or underlying driver now contains global variables, or if this driver data or the driver simply requires global data, then we can also define the output section in which this data lies. And once we have defined this, we can associate the runnable with this protection set. So if I would now generate this system, then the access rights required for this UART functionally, or the access rights as they are defined in this protection set, are associated with the runnable. So every task executing this runnable now would be aware that access needs to be granted to this protection set. The last feature I want to show in this video is located in another project. So let's first clean up. So I'm importing the system states example. And again, in here we have the LED signal flow as well as the UART signal flow. And what this model shows and what this code shows is how to use several system states. So in one system state, the LED shall blink, and as soon as a button is pressed, the system state changes, and in that second system state, the LED shall be on all the time, but more important, this UART runnable shall execute cyclically with the same frequency as button state. So once again, our 200 milliseconds. So in here, for the run UART send, this is only active in the UART state. However, this run UART wake up shall be only active in the blink state, and the blink state is, in this example, the initial system state. So the idea is, as soon as we have a positive edge on the button, this runnable gets invoked, switches the system state so that this runnable cyclically gets activated, and as soon as the button is not pressed anymore, it shall switch back to the blink state. What has to be done in order to allow those runnables that they can change the system state is to set this returns flag here, which will change the API of the runnable in such a way that it can create so-called state change requests. In code, this looks as follows. For the runnable wake up, it doesn't have, let's have this side by side, it doesn't have any parameters other than the trigger port. And as soon as it gets activated, okay, it sends directly an UART frame, but most important, it returns a value. So in ordinary runnables do not return a value, but those who can change the system state return a value. And there is no particular error or something, so there is a return type or return value which is simply a state change request. And as soon as the runnable has returned a value other than OK, the so-called state handler will be called, and it will not be called in the same context as the runnable, but it will be executed in the context of the central activation engine. So all the runnables returning a value other than OK will create a message. This message then is queued within the central activation engine and then processed one request after the other. Up here we can see, for the state handler, we can see the runnables, those two, the send runnable and the wake up runnable, that those two potentially could send state change requests. And within the state handler, we not only get the current system state, but also this state change request state message, in which meta information is stored about the runnable returning a value other than 0. So for example, in here we could see that the runnable, or for this event here, we could see that the runnable UART wake up returned such a state request. we can see from which task this was sent. If the runnable was triggered by a signal, we could see the signal in which triggered the execution. We can see what kind of event triggered the execution of the runnable, at which time did the state change request happen, what was the system state within the runnable when the state change request was placed, and what was the result of the runnable. So within the request, I implemented it here at a simple switch case. So in here, I simply say if the runnable returning any value is, or if this run UART wake up returns any value other than 0, then I simply transition into the UART state, and I do this transition here simply by directly returning the desired state. So the return value of this state handler is the desired new state. So this will simply now switch the system state. And within the run UART send, I basically do something similar. I say, so up here I have all the logic to send out the UART frames, but I say once the button state data is full, so it's not pressed anymore, I return this state change request. So if the runnable run UART send returns state change request value, then I switch back into the plink state. If it returns a value other than that, so in my implementation here, those are all error messages, then here I simply, for debugging purposes, inserted a breakpoint. I also have the possibility to visualize the system states. So here in system states, I can create signal flow diagrams, which are then task-based, not data-based, but task-based for every system state. So for example, in the plink state, I can see that the button state is acquired from hardware and sent to the LED runnable, while in contrast for the signal flow for the UART system state, I can see that I additionally have this run UART send runnable being active. The peripherals and the details as they are seen in here can also be adjusted with this layers feature. One last feature I want to show is the use of plantUML diagrams. There are multiple locations throughout the system or throughout the model in which you can create such diagrams. So for example, for all the software functions, but many more. And I want to briefly show this for the example of system states. So here such a diagram has been created. It has a name and a description, and it has its plantUML code, which simply describes an state diagram. And if you have valid plantUML code in here and you generate the report, then within the same location you can see the diagrams as they have been generated or translated. If you're not familiar with plantUML, you can simply go to plantuml.com and play around with it, make sure that the syntax is correct, and learn a little bit about this library. All right, that's it so far from my side. Have a nice day.